Welcome. In this video we're going to talk about everything there is to know about electron configurations and how to write them. These configurations are used to denote where electrons are located in an atom, and they vary from element to element. So first let's go over some basic information you need to understand in order to be able to write an electron configuration. First, most important thing you need to know is that there are 4 different principal energy levels, and they're denoted by N. So we can have N equals 1, N equals 2, N equals 3, or N equals 4. And within each of these energy levels, we have 4 possible subshells as well. And these possibilities are the S subshell, P subshell, D subshell, and F subshell. And each of these subshells has various numbers of orbitals. So the S subshell has 1 orbital, the P subshell has 3 orbitals, the D subshell has 5 orbitals, and the F subshell has 7 orbitals. And each orbital has 1 pair of electrons. So a 1 pair means 2 electrons. So each orbital has 2 electrons in it. So S orbital will have, the S subshell will have 2 electrons. The P subshell will have 6 electrons. We're just doing 1 times 2, 3 times 2. The D subshell has 10 electrons, and the F subshell has 14 electrons. When we're writing an electron configuration of an element, we need to know which one of these subshells to use and in what order. So you might be wondering that. Well, we can turn to the periodic table for this. The periodic table is conveniently organized into the various subshells, as we can see in this image. It's also organized in a way that we can see how many electrons each subshell has. So we have the S subshell over here, and we have 1, 2. So that means there's 2 electrons. We have the 2S subshell. 1, 2 electrons. We have 2P. We have 1, 2, 3, 4, 5, 6. From B to NE, we have 6 electrons. And that just shows everything I explained before. You do not have to memorize it because for most exams, you'll be given a periodic table, and it's broken down right on the periodic table. So using the periodic table, let's take an example and let's try to write the electron configuration. So say we are asked to write the electron configuration for sulfur. Let's get started. We're going to go from left to right, left to right, left to right, down each group on the periodic table in order to write this. So first we have the 1s subshell, and in this subshell we will have 2 electrons. We have He and H. Then we will move down to 2s. We have lithium and beryllium. So once again, we're filled with 2 electrons. Then we're going on to 2p. As I said, 2p has 3 orbitals, and each as denoted by these lines. And each one of these orbitals has 2 electrons. So we're going to fill in these electrons. Next, we're going to go to 3s. We have Na and Mg over there. So we have 3s, and I'm only going to have 1 dash because the S subshell only has 1 orbital. We have Na and Mg. We're going to fill up those 2 electrons. Then we're going to go on to 3p, which once again, 3 orbitals. And we're going to stop at sulfur because we're only writing up until sulfur, right? So 1, 2, 3, 4. We're only going to include 4 electrons this time instead of all 6. So 1, 2, 3, 4. And notice how I wrote that in a specific manner. I wrote singular electrons first, and then I started pairing them. So I didn't do this, 1, 2, 3, 4. This is wrong. And this is wrong because we have to follow a principle called Hund's rule. And just to reiterate, Hund's rule states that electrons only pair up after all orbitals are filled with a single electron first. So, like I said, just kind of a replay. we're only filling in 4 electrons, so we're going to fill it like this. First single, first single, first single, and then we're going to start pairing. So this is how we're going to write it. And this is going to be the same for any electron configuration you write. You must follow Hund's rule. So I recommend that even when you're filling up orbitals in which all of the electrons are present, still write them in a way that they are unpaired first and then pair them. So you will never forget to use Hund's rule. And I actually have a tip for remembering this, which I'm going to steal from the Kaplan MCAT General Chemistry book. And this tip is that try to imagine it the way people sit on a bus. So first everyone's going to try to get an empty seat on the bus. But once all of the empty seats are filled with one person, the next people on the bus are going to have to start pairing up with those people who are already sitting. And that's exactly what's happening with these electrons. Another rule that we need to remember is called the Pauli exclusion principle. And that's what this is. So you may have noticed that every time we write the electrons, we write them in this manner. One is pointing up and one is pointing down. This is always the case. We can never draw electrons like this or like this. One must always be pointing up and one must always be pointing down because of the Pauli exclusion principle. This principle states that paired electrons must always have opposite spins. So one pointing up and one pointing down is what denotes those opposite spins. Those are the two major rules that you need to remember. But one thing that might get a little bit annoying is to have to draw out this whole entire thing, all of this, every time we try to do an electron configuration. So lucky for us, there is a shorthand. And the shorthand is to just write it out like this. 1s2, 2s2, 2p6. So, as you can see, the exponents are the numbers of electrons that we're filling. 3s2, 3p4. So let's put it together, and it's going to be written like this. And this is the shorthand electron configuration for sulfur. So we don't have to draw these arrows and spins every single time, but you still need to understand where we're getting it from, and that's why we went over it. Another extremely useful shorthand is the noble gas shorthand. So instead of writing all of this for sulfur, we can use the noble gas that comes in the period before. So in this case, that would be neon, because it is the previous noble gas that comes before sulfur. And we can put Ne in a bracket and then just add the 3p4, which is where the sulfur is located. And this would be the noble gas shorthand configuration for sulfur. This is another shorthand that can come really useful when we don't have enough time to write down every single thing. So this is just the basic information on how to exactly write these electron configurations, the various rules that we need to keep in mind, and different shorthands as well. And now I just want to go over two different quick classifications. One is called diamagnetic and the other is called paramagnetic. So if you noticed, for sulfur, in the final subshell, we only had 4 electrons instead of 6, so some electrons, such as these, went unpaired. And when some of these electrons go unpaired, it's called paramagnetic. And when something is paramagnetic, the electrons will be pulled into a magnetic field. So I like to remember this with paramagnetic starts with a P, and pulled starts with a P as well. So it will be pulled into an external magnetic field. And you might have guessed it, diamagnetic is the exact opposite. So say we had argon. In argon, all three of these orbitals are filled, so we will have 6 electrons. And we don't have any electron that is going unpaired. In other words, all electrons are paired. This means it is diamagnetic. And that is the exact opposite. These electrons will be pushed away from an external magnetic field. So there you have it. Those are the basic concepts you need to understand about electron configurations.